Welcome back to the Formulaic Approach channel. In this video, we are going to discuss most of all you need to know about alkanes. Okay, all right. So the following are what we will cover. We will talk about what alkanes are, then we'll proceed to petroleum, which is the raw material that produces alkane as well as other hydrocarbons. Then under petroleum, we'll just talk about briefly its composition and the process of fractionation or fractional distillation. Then we'll talk about the after the petroleum, we'll talk about octane number, still under petroleum. We'll talk about octane number and cetane number. Then we'll now talk about the physical properties. Then we'll talk about the methods of preparation, and then we can now we'll finalize with the chemical properties. Okay, so this is basically what we'll cover, all right, which is most of what you need to know about alkanes. But in this video, I will not be covering nomenclature because I have already done that in previous videos, so do well to see the link in the description. And I've also done a summary video of Organic Chemistry 1, so I'll also link that in the description so that you see. But we are going to do in-depth study on alkanes today. So what are alkanes? Now, alkanes are basically defined by a number of things. Number one is saturation. So alkanes are saturated hydrocarbons. And what does saturation mean? It means that they contain just the maximum amount of substituents or group that should be attached to them. Maybe hydrogen throughout or substituents, but in as much as it is all the four bonds that are captured around it, then it is saturated in single bond straw rather. So saturation, they are saturated and they contain all single bonds that are all sigmas. They are all sp3 hybridized in essence. They are sp3 hybridized, are full of single bonds that are all sigmas. Then they are aliphatic. They could be aliphatic, they are not aromatic, okay? They could be aliphatic, cyclic or acyclic. Okay? So these are the basic terms that define alkanes. Single bonds, saturation, sp3 hybridized, aliphaticity, whether cyclic or acyclic. Okay? And the aliphaticity could also be branched or straight chain. All right. So now that is what alkanes are, and they are generally known for their weak reactivity. Hence, they are called paraffins. Okay, they are commonly called paraffins, and the word paraffins comes from two Latin words, parum and affinis. Now, what does parum mean? Parum means weak, okay? Param in itself is actually from the word para, and in science, or in Latin actually, para actually means when something is not exactly equal to something, but it's almost equal to that thing. So we say it's close to it, so that's para, okay? Close to it. So that's para. So param here means weak, okay? Then affinus refers to attraction, love, okay? Wanting to coordinate, wanting to, attraction, okay? So we just use the word affinity, which means love, okay? So they are called paraffins, which literally means weak affinity. So they have weak affinity. So that's why under normal conditions, ordinary conditions, they don't react with other reagents, okay? So it takes you to bring in a catalyst, you just take special conditions for them to react. All right. So that's that with alkanes. So they also have the general formula CnH2n plus 2, CnH2n plus 2. All right. In the video that I said you should see in the description, I have talked about the kind of formulas that we have, molecular formula, and all of those things in the homologous series. Okay. So you can see that video to understand what we're talking about here. So, but basically, this is their general formula, general molecular formula. Right now, so where are alkanes gotten from? Alkanes are basically part of the unit of fractions of petroleum. Okay, so petroleum is basically an oily, inflammable liquid. Okay, that is also usually thick. All right, it's gotten below the earth crust. In fact, the word petroleum actually comes from two Latin words too. From geography, Petra means rock, and oleum means oil. So it just basically means oil that is hidden under the rock, all right? So that's petroleum. Petroleum contains many hydrocarbons and other constituents. In fact, non-carbon compounds, okay? Compounds of oxygen-containing compounds, nitrogen-containing compounds, sulfur-containing compounds, and it is even known that about more than 500 compounds can be identified in some petroleum fractions, depending on the region where they are found. Okay, so USA is the highest oil producing country. I think followed by Venezuela or something. Russia, even Nigeria will also produce petrol. Okay, so that's origin. So then in composition, we know that our natural gas, okay, natural gas is one of the constituents of the petroleum, and natural gas is made up of chiefly methane, okay, about 80% of it is methane. Then about 10% of it is ethane, and another 10% is the higher alkanes. Okay, the higher alkanes are the remaining. So it means that it's chiefly these first four products: the alkane, the methane, ethane, propane, and butane. Okay. So and our LPG is gotten from it. So now let's talk about the fractional distillation of petroleum. So we know that the petroleum that we get is in the crude form, hence the name crude oil. So, and it cannot be used in that form. So it has to undergo a process known as refining. So the first stage of refining is fractional distillation. Fractional distillation. Okay. Now, how does fractional distillation occur? Fractional distillation, first, what is distillation? A chemical technique that we use to separate substances that have different boiling points, okay? All right, so fractional distillation is, since we already know that petroleum contains different fractions, and there is a chamber where different fractions of petroleum, after heating or on heating, gets to be separated by themselves into various layers of the column. So now let me give you the rough sketch of what happens. So we have a particular furnace here, okay? We call this place the flash chamber. And it's called the flash chamber because a process known as flashing occurs there. And what is flashing in this context? Flashing is just how that the petroleum, the crude oil, is passed into this place, okay? And as it is passed into this place, it gets expanded quickly, okay? The expansion occurs quickly, and that's why it's called the flash chamber. So after expansion of, why is he expanding the crude oil? Is for vaporization, so that it vaporizes quickly, and on vaporization it's going to pass through here. So what you have in here is going to be the vaporized crude oil. So the vaporized crude oil is going to be passed into another chamber here, and this is called, it looks like a tower, so it's called the bubble tower. It looks something like this, but there is an outlet here, okay. So this is our bubble tower. Our bubble tower, because everything is bubbling there. All right. So now, what happens in the bubble tower? So the bubble tower is made up of different compartments. Here also, in order to reduce pressure, steam is passed into this place. So steam is passed through here. Okay. Then there's also an outlet here for our residue. Okay, so inside these bubble towers, there are bubble caps or bell caps that are arranged on bubble tubes. Okay, bubble tubes are inside trays. Okay, they are called trays or plates. So the trays are such, they are arranged like this. You have something that looks like this. Okay, so these are bubble tubes arranged on the trays. Okay, these trays are just they are in different columns based on the fractionation, the fractions that want to get separated. Okay, and there are tubes that we call downcomers. There are tubes that we call downcomers through which, you know, the fractions that are first, what are the trays for? Now the trays are to collect condensates. The process that it uses is that the mechanism it uses that after the vaporization here, those vapors rise, okay? You know, they are already at high temperature. So as they rise, okay, the temperature becomes lower at the top. Okay, does that make sense? So as the temperature is becoming lower and lower like that, the ones that are less, that are more dense will be condensing at the higher temperature here. The temperature is increasing as you go up. The temperature is decreasing rather as you go up. So the one with less density, the less dense ones are going to get up to this point or at the higher portion of the column, and the one with low densities, the one with high densities that condense quickly, okay, they are the higher fractions. They are going to be collecting at this point. So what did I mention here? I said there are going to be bell caps on these bubble tubes. Now, what is the axis of the bell curve? After expansion here, now, so that these guys don't just rise up and then just condense like that. The expanded gas does not just rise up and get to each column and just stay, okay? Because they might be mixed up if that occurs. In order to avoid for the mixing of those gases arbitrarily, there is those bell caps will provide room for further expansion, okay? So inside these tubes, bubble tubes, are the condensates. So the vaporized gas is now going to make its way into that place, so that the vaporized gas mixes with or bubbles through. Actually, that's why it's called the bubble tower, the bubble tubes. So it bubbles through the condensate, and by bubbling through the condensate, there is a complete separation of the fraction that can be distilled at that level, okay? So actually, you now have tubes that go out where those are different layers, they will be collected, okay? Now those tubes are actually not straight, they are like troughs, because they are going to be collected, like flow into the tube, okay? So at the higher end here, we have volatile gases. Volatile gases will come out from here. Then our gasoline is going to come out from around here. Gasoline is going to make its way out here. Then we have around here, we are going to have our kerosene. So keeping in mind that the density increases as you go down here. So these ones are volatile. So high volatility as you go, volatility increases as you go up, and density decreases, while volatility decreases as you go down and density decreases. And these ones I'm writing, okay? So this one, kerosene is denser than gasoline, okay? Diesel, on the other hand, is denser than this guy, right? So diesel is going to be collected at a lower end of the fractionating column. And at this column here, what you have is your oil, okay? Your lubricating oil, for example, lubricants, for example. Okay, now it is not lubricants, just lubricating oil. Lubricants because there are other things that they add to lubricant to become that lubricant, okay? So, but the portion that becomes your lubricant, that is used for your lubricating oil, gets around here. Then there's a tube that passes here, which collects the residue out. All right, so this is basically the way the fractional distillation of petrol takes place. Okay, now let's talk about the octane number. So now gasoline is chiefly what most of our combustion engines use. Okay, so we'll talk about octane number and cetane number. Let's first talk about octane number. So, like I said, gasoline is is the most common fuel that our internal combustion engines use. Okay, so and the quality of the gasoline is based on the octane rating. That's another name of that fuel. So some fuels have high octane rating, which means they are very good fuels. Okay, now first, the way we define it, I'm going to give you the technical definition and what it literally means. So what it first literally means is octane rating is just a measure of the anti-knock property of a fuel. So a fuel with high octane rating is going to, the tendency of it knocking your engine is low, okay? It has high anti-knock property and or high detonation so it has so a fuel with high octane rating has high anti-knock property. Another name for knocking is detonation, okay? Because it's detonation or detonation that occurs in the internal combustion engine. So my point is that now the octane number is the measure of the quality of the fuel. Okay, so technically we define octane number as the measure of the percentage of iso-octane. This is it. The best fuel is giving octane rating of 100, and iso-octane is what sets the standard. Okay, so iso-octane has the highest anti-knock property and is giving the 100 octane rating, 100%. Then N-heptane is giving 0. It's a very bad fuel. So octane rating that is given to your fuel or given to any fuel is the measure or the percentage of iso-octane. That the IUPAC is 2,2,4-trimethyl pentane, yeah? 2,2,4-trimethyl pentane, iso, 1, 2, 3, then 5. So 2,2,4-trimethyl pentane. So is the measure of the percentage of this iso-octane that is available in the mixture. So this is what they do. They will create a mixture of iso-octane and N-heptane, okay? Because that is the chief product of your fuel that you're using, okay? So that the mixture of that is created of that iso-octane and N-heptane that will have the same ignition property as your fuel is the octane rating of your fuel. Does that make sense? Okay, so the percentage of that iso-octane that is available in the mixture that they make. That mixture they make is going to correspond with the ignition property of that your fuel has. Okay, so the percentage of octane, iso-octane that is available there is going to be. Do you understand now? All right. So generally, the factors that affect octane rating, they include the number of branching or substitution, degree of branching. Okay. So if for a more substituted alkane, it's going to have a high octane rating. The more the substitution, the higher the octane rating. So for example, if I were to ask you between butane and this guy, which of them is going to have a higher octane rating? Is it butane or methyl propane? This guy, yes, because it is branched. So the higher the branching, the higher the octane number. All right. Another thing that affects octane rating is saturation. Okay, saturation. So if when there's an unsaturated hydrocarbon, when there's an unsaturated center or a carbon that is unsaturated in your molecule, that guy is going to have a higher octane rating than a corresponding saturated hydrocarbon. Does that make sense? Let me give you an example. For example, I have here, look at this, my guy now. CH2, 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 CH3. This is butene, right? So if I have butene and butane, who is going to have a higher octane rating? Butene. Yeah? Why? Because double bond, sorry. Yes, because of unsaturation. Now, another thing that affects, this one lowers octane rating. That is the length, okay? The length of your carbon-to-carbon bond. So the longer the carbon-to-carbon bond, the lower the octane rating. So if I clean this now, which one will have the highest octane rating? This guy or this guy? This guy, yes. Because the length with the number of long chain, because we already said about branching, yeah? Branching also helps or increases the distance. But this one is not branched, but because it has lower number of carbon, it's going to be it's going to have a higher octane rating than this guy. All right. Another thing is cyclization. If the chain contains a cyclic hydrocarbon, then it's going to have a higher octane rating than a corresponding alkane. For example, it means that cyclobutane is going to have a higher octane rating than butane. Does that make sense? All right. So now let's talk about cetane number. Okay, generally here, our fuels, they are graded based on their octane numbers. If you've heard of, I saw one man, that's what I remember. He said you cannot buy fuel in a particular petrol station because their fuel is bad. Okay? And every other person is buying fuel there. Okay? Now you understand what he's saying because the kind of automobile he was using or the car is using is probably a very, I don't know, I would say very quality one. Just permit me to use that because according to him, that way, so according to him, if the octane rating of this thing, the internal combustion engine, takes octane petrols with octane rating greater than about 87 to 95. Now, if you give him a regular fuel has octane rating of about just 75, and third grade low class fuel has lower than 65 octane number. So if the octane number is around 75, that's for regular fuels. If you pour that kind of thing for an internal combustion engine to his own in his own car, it's just a matter of time, it will knock. It doesn't really knock immediately. Okay? All right. So that's that. Now let's talk about cetane number. Cetane number. Now cetane number is just like the opposite of octane number, only that it's okay. I won't say the opposite. Why I call it opposite is because they are applied for different engines. So this one is for gasoline engines, okay? This one is for a certain number is used for diesel engines. Engines that use diesel, okay? The reason why I've called it the opposite is like it's the reverse. Now here's the case. Here 2,2,4-trimethylpentane sets the standard, but in this case, cetane rating of 100 is given to this guy, hexadecane. Hexadecane. And where is hexadecane? C hexa, that's 6, decane, that's 16. So that's C16, H32, 34. Plus 2, right? 34. Is correct, right? So hexadecane sets the standard. So this one is given octane rating of 100. Okay? So if your diesel is just practically this, then it has 100% cetane number. But this other guy, alpha methyl naphthalene, alpha methyl naphthalene is giving octane cetane number of 0. Okay, so classically we will say that the cetane number therefore is the degree or percentage of hexadecane in a mixture of your hexadecane and alpha naphthalene fuel that has the same ignition property as your, should I write it on the board? Yeah, I'm going to write it because like that's the standard definition, okay? It's the same for octane, octane number, only that we change the what set the standard and the mixture. So the cetane number is the percentage of hexadecane in a mixture of hexadecane and alpha methyl naphthalene in a mixture of this and alpha methyl that has the same ignition property or combustion property as the fuel that you are considering, the fuel under consideration or examination. All right, so that's for Cetane number. Basically, the Cetane number is not usually high. Okay, once your Cetane number is greater than 45 or 50, it can work for any diesel engine. Okay, so that is that on Cetane number. Okay, the factors that I talked about. Now this one, the higher the branching, the lower the Cetane number. It means that a highly branched alkane is a bad diesel engine fuel. Is a bad diesel for diesel engine. Which other thing? Length. Now, the length of the carbon to carbon chain also. Once the length the carbon once it's long enough, then it will have a high Cetane number. Does that make sense? All right, so that's about octane and Cetane number. Now let's go to the physical properties of alkane. What are the physical properties of alkane? So basically, when we talk about physical properties, we talk about appearance and taste. You know, the way I usually say your eyes, what you can see, what you can smell. Okay, we don't taste alkane. So in physical properties now. Now, physically, the C1 to C5, guys, this one, or C4 rather, they are primarily gaseous. Then C5 to C17, they are liquids. So what do you see? Then so greater than C18, greater than or equal to C18 from C18 above, the what? Solid. So what do you see? That the density increases as you go down the homologous series. So, and I'm going to talk about that one. Okay, yeah. So there's something that came to my mind now. So like this, you see this in the trend. That's for the physical appearance. They are colorless and odorless. So they are colorless and odorless. Okay. Now let's talk about their solubility and their boiling point. First, let's talk about their solubility. Now, they are generally insoluble. In fact, covalent compounds, you know, they are generally insoluble in polar solvents. Yeah. So these guys do not dissolve in water, which is our universal polar solvent. Okay. So since they don't dissolve in polar solvents, it means they will dissolve in non-polar solvents such as benzene, ether, naphthalene, toluene, phenol, etc. Okay, so these guys are soluble in these guys, but insoluble in water. Now, why are they insoluble in water? And the reason is because they are weakly polar. Actually, we usually say that they are non-polar, that the covalent bond between them is non-polar. And that is correct because, now, number 4, we are going to be talking about boiling point. Now, listen, it is correct to say that they are non-polar, but actually, if you want to be specific enough, they are actually not non-polar. They are actually polar a bit, okay? Only that carbon to carbon bond, because they have the same electronegativity value. According to this guy, Pauling scale, these guys, carbon, have electronegativity value of 2.5. So 2.5 and 2.5, what is electronegativity? It's pull on electron, right? So they have equal pull on electron, which means that the dipole moment here is going to be nice, smooth, right? That is, there's even distribution of electron. Yeah. So, but C to H bond, on the other hand, is we usually say it's not polar, but it's actually weakly polar. And what do I mean by weakly polar? According to Pauling scale, carbon's electronegativity value is 2.5. Hydrogen electronegativity value is 2.1. Generally speaking, once the electronegativity value is greater than 0.4, we say that the bond is polar, which means that there's going to be a significant intermolecular force that will affect the physical property of that compound, of that molecule. So, but for this guy, this thing is just 0.4. Okay, so does it now mean that it's not polar? It is actually polar, but weakly polar. So which means that there are still weak intermolecular forces. So since there is weak intermolecular force, apart from this bond, if there is weak polarity, then it means that there's going to be a weak intermolecular force. So they will require energy, therefore, to first break the bond, the carbon to carbon bond, the carbon to hydrogen bond, then further energy to break the carbon to hydrogen bond that will form in between intermolecular force. Okay? So because what that means is that this is going to gain a partial negative charge because you have a higher pole being highly electronegative, not highly, but relatively highly electronegative than this guy, which will have a partial positive. So we are going to have, so where we have another C to H bond somewhere, then this is going to be slightly positive. So this guy will seek to coordinate to this guy, although weakly. Do you understand now? So what that means is that since there is high intermolecular force, then the boiling point is going to be high. Now, what are the things that increase the intermolecular forces? When the carbon to carbon chain is long, so the higher the carbon to carbon chain, then the higher the intermolecular force. I do know IMF, Impossible Mission Force. I don't know that movie. You don't know Tom Cruise? Let's go. It's a movie. Okay, anyways. So the higher the carbon to carbon chain, the higher the intermolecular forces. Why? Because there are more interactions happening here. So, and of course, the higher the carbon to carbon chain, there's also what? Higher surface area. Okay? So once there is also higher surface area, then there is what? Higher boiling point. Okay? There is higher surface area means that there is going to be space enough for them to interact more. Okay, so it means that the intermolecular force will also what? Increase. All right. But once there is a branching, okay, branching reduces the surface area. Once branching is high in your alkane, then your surface area will decrease, which means that your intermolecular forces will also what? Decrease, because the higher the branching, there is steric hindrance. We call it steric hindrance. Steric hindrance means hindrance due to bulky molecules surrounding your atom. Okay, for example, look at this guy, CH3, 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 and look at this other guy, CH3, CH3, and H, and look at this last guy. Now, if you look at this one is more substituted than this guy, right? This one is more substituted than this guy here, okay? So as it is like this, there is steric hindrance here higher than we have here. Here, there is no steric hindrance at all, in fact, because the molecules that are there are not bulky. But here, there is steric hindrance, a little bit of steric hindrance, so which means that if anything wants to attack this thing, I opened this place here because I'm still going to talk about, when we talk about their reactions, I'll teach you mechanism. Mechanism is very simple, okay? But I will not go into whether it is SN1, SN2, the type of mechanism it is, okay? But I'll just show you how to draw it. Now what happens is that once something wants to attack it can come and attack where there is less bulky molecule, okay? But this one, nothing can attack this thing. This thing can stay like this, okay? Even when We call this a carbocation. Don't worry, I'll show you what that is. So my point is that this guy is more substituted. So because of that, there is lower surface area, and for which reason there is reduction in intermolecular interactions that could have taken place. Okay, keep in mind intermolecular interaction, not intramolecular interaction. Inter. All right. So the higher the branching, the lower the boiling point. The higher the branching, the lower the boiling point. The higher the carbon, the higher the intermolecular forces, the higher the surface area, hence the higher the boiling point. Okay, but actually you also see in that trend, so it means as you go down the trend, you are going to see what? Increasing boiling points. As you go down the trend, we also see increasing boiling melting point. But here is the problem with melting point. Once you begin to see carbon 14 to carbon 16 to carbon 18 to carbon 20. Now I intentionally mentioned these ones that are even number because that's where the inconsistencies begin. Now even number heavy hydrocarbons, they tend to have higher boiling points than odd number guys. The reason is this, from here, I said that from this guy, you begin to see solids, right? So with solid hydrocarbons, there is higher packing, higher compactness, okay? They are able to pack well, okay? So, pack well. So because they pack well and interact well, because of better interaction, okay? Because okay, think of this thing as because they have the same this thing height, these two markers, they can pack well together, okay? They can bond together perfectly and you will not know that there is this thing. But look at this guy, look at these two. One is taller, yeah? Okay, because of that difference in height, there is a center that is available for interaction, kind of, okay? So because of that, there will be what? Low melting point, yes, for alkanes that are odd number. So odd number alkanes that have odd number odd number carbons. They are going higher alkanes that have odd number of carbon. They are going to have lower melting points than their close even number. Does that make sense? All right. So that's the inconsistency in this thing. There was something I wanted to mention that I just remembered now. Now, when we're talking about octane number, there are a number of things that they use to increase the octane number of this thing. So one is this tetramethyl lead tetramethyl also. Tetramethyl lead. Okay. They've banned the use because of environmental issues. Okay. So now we've talked about the physical property. Now let's go to the methods of preparation before we see chemical properties. Now I'll bid you to listen in the method of preparation because this is where questions are usually asked the most. And the thing is, I will not be covering alkene tonight because there's something else I still want to shoot. But tomorrow I will cover it. Doesn't mean you have to be here, okay? I'll send you the video. All right. What else I want to cover? Methods of preparation. Now, the methods of preparation of alkene are, there are many, okay? Or we are going to be treating maybe 4 or 5. Let's list the amounts that we can. Okay, so we have let's start with the Clemenson reduction. Clemenson reduction. Then we have the Wurtz reaction. Then we have the Kolbe electrolytic process. If you have seen that video that we've covered, I think this and this before on that series, Colby electrolytic process or electrolytic method. Okay. There was one question that I saw when I wanted to do this in an online class with one of the boys I was teaching. So they now asked that which of these is not a method of preparing alkane. So then they mentioned this process, Bergius process. Now Bergius process is not a method of preparing alkane, but it's a synthetic method of preparing petroleum. Okay, Bergius process. We actually have two synthetic methods that I know though. Now what the Bergius process is it involves hydrogenation of coal tar, coal, hydrogenation of coal. So then to form petroleum. Then there's, I think, the Fischer-Tropsch process. Okay, this one too is not a method of preparing alkane, it's a method of preparing the petroleum. Okay, like crude oil, making crude oil. Okay, this one involves, both of them involve hydrogenation, but this one hydrogenates coal, this one hydrogenates water gas. So under high pressure and temperature. Okay, so my point is we have the Colby electrolytic process, we have the hydrogenation. Okay, this one is also hydrogenation, right? It's a special type of hydrogenation that I'm going to talk about now. Hydrogenation of alkyl halide. I think this is where we will start. Alkyl halide. We'll start with this. Then there is also the decarboxylation reaction. We've covered this too before. Then there is also decomposition of Grignard. Remember Grignard? Grignard reagent. Okay, so let's start with, there's also this guy, Clemenson reduction is analogous to this one, Wolff-Kishner reduction. I'll talk about them together. So with this, let me show you, I said I'm going to show you mechanism a little bit. Let's start with the hydrogenation of alkyl halide. All right, hydrogenation. Now, how does hydrogenation of alkyl halide occur? So we'll be writing this. Let's write the general formula first. So this is an alkyl halide. Okay, so plus hydrogenation, that's H2. Okay, so what do we have? At the end of the day, we'll have R. This guy is going to add to this hydrogenation of alkyl halide. So what will happen? This guy will alkyl halide. What will happen? Hydrogenation of alkyl halide. Not alkyl halide, of alkenes. Alkenes. Alkyl halide is Ward's reaction. Alkyl halide is Ward's reaction. I'll show you what. Come on. So hydrogenation of alkenes. Now if I have R double bond R plus hydrogen. Okay? Alkyl halide. If I use that, that's already an alkene. Okay? But hello alkene though. So that's why it's not correct. So this is it, hydrogenation of alkane. This one is reduction of alkyl halide, that's what we call it. Reduction of alkyl halide. So we have hydrogenation of alkenes. So for this alkene now, hydrogenation of alkenes. Let me change that. So this is my alkene now. Now it wants to be added on to hydrogen. So we're going to have R R. Okay. Now, here's how it happens. For example, if I have this guy, ethene. Okay. So what happens is that when we had our hydrogen, this one is going to break the bond, attach here. This bond is going to break the bond and attach to this side. Okay. Now this is called an addition reaction. Okay. And it's specially called a syn addition reaction. Now, why is this syn? Syn is synchronous or syn, whatever. Syn means the same side. Okay? Syn addition reaction. Why? Because these two hydrogens are going to be attached on the same side. So what we'll produce at the end of the day will look like this. These are the two hydrogens that were attached before. These two. So these two hydrogens will now come here. This is the first one. This is the second one. So they are attached on the same side. So that's a syn addition. Now I need to mention this because when we now talk about halogenation of alkene, we'll talk about that when we get to alkene. Okay? And we'll talk about hydrohalogenation. So with halogenation now, with halogenation of alkene, we call it regiochemistry. The regiochemistry is different. The kind of addition that takes place is an anti-addition. Anti-addition. So what is anti-addition? So we still want to add to this guy our ethene. Yeah? So we still want to add, but this time we are adding halogen to this side. So this guy plus Cl2. I like to put it in bond form, okay? So what happens is that once this guy gets attacked, what we produced is something that looks like this. So our two hydrogens, let them come here. Then we have something to be attached here. Our two hydrogens, one comes here, the other comes here. Something be attached here. Okay. Now what happens is that we cannot have this. That's what I'm trying to say. This is still syn addition. So what we'll have is an anti-addition such that H will come here, Cl over here. Can you tell me the reason? Do you remember Vespa? Can you use Vespa to explain? Now you know that Vespa theorem talks about how the geometry of this guy, their regiochemistry, how they tend to want to arrange themselves. So according to valence electron pair theory, that they will tend to stay as far away as possible from each other. If they must maintain the bond angle between, for alkanes, I didn't mention, is 109.8.5 granules, right? Or 109 degrees 28 minutes. So if they want to maintain this bond angle between them, their tetrahedral geometry, they have to stay as far away as possible, because these guys, chlorine, when they come together here, they are going to repel each other. Okay, so the farthest away they can stay from each other is in the anti-conformation. Do you understand? All right. So that is that about this. So other types of addition. So if you're not thinking of what of hydrohalogenation, if it were hydrohalogenation, the conformation does not matter. Okay, what determines the position is the Markovnikov rule, and I'm going to cover that with you in alkene. The Markovnikov rule, that one sets what will be and what will be. Do you know the anti-Markovnikov and Markovnikov? Okay. No worry, we'll talk about it. All right. So that is that for this guy. So this is the way we form this thing using hydrogenation of alkenes. So the second one we want to talk about is reduction of alkyl halide. Reduction of alkyl halide. Now, how does this reduction take place? How does the reduction take place? So we have an alkyl halide. We have an alkyl halide. And in the presence of sodium, okay, actually, the reaction takes place in the presence of dry ether because, as you know, sodium is vigorously reactive to water, so it has to be dry. So when they combine, they do their thing, you're going to have R will combine with another R, so we have two R's. So in fact, the best way I write this is Rx plus Na plus another Rx, okay, plus 2Na this time, so you're going to have R will combine with R, like that's how to just picture it. And X will come together with this guy, then you have NaCl. Does that make sense? Okay. So, and since that makes sense, we don't need, okay, now there's something about this. Usually the best, this reaction, this one, is called the Ward's reaction. It's called what? Ward's reaction. Ward's reaction. All right. Now, I wanted to say something here. There is a catalyst here. The catalyst here is dry ether. The catalyst here is platinum or palladium. Okay? Platinum or palladium. Palladium is PD, eh? Platinum or palladium. Now, there is a special type of hydrogenation that is called the Sabatier-Sanderson. We even made it into a song in that video. Sabatier-Sanderson reduction. Okay, so this one uses nickel, but at a higher temperature and a higher pressure than this. Is that clear? Okay, so that's for a special type of hydrogenation that uses nickel catalyst, Sabatier-Sanderson. This one is called Ward's reaction, and it uses dry ether as its catalyst. Okay, so here's what happens. Basically, there is the cleavage of this bond, the mechanism, how it occurs. Okay, there is cleavage of this bond. I'm going to use one. So what kind of cleavage will occur here? The cleavage that will occur here is, there are two types of cleavages, or fission. We have the homolytic fission and the heterolytic. Did you see that video? Okay. So it is, because there are two different atoms here, what will occur here is heterolytic fission. So what happens is that this guy is going to take on, we draw with two arrowheads, you remember? Two arrowheads to show that the two electrons are taken up on by one person, one atom rather. Okay? So at the end of the day, what we will have is that this guy will be positively charged, a carbocation, and so this guy, R plus, is called a carbocation. Okay, now you must understand, let me explain what carbocation is. Carbocation is just a carbon atom that has a positive charge. Okay, now there is something with these carbocations. So with this thing I wrote here, this one is very unlikely. Do you know why? It's unlikely because this carbocation cannot form. Why can it not form? Because it will not be stable. Now, the stability of carbocation goes like this. It starts with methyl. So a methyl carbocation is very unlikely. I can't say it is totally unlikely because I've not carried out an experiment on it before. But it's very unlikely because of the stability. For it to be stable, this way it is. This one is less stable when you compare it to a primary carbocation. This one is less stable when you compare it to a secondary carbocation, and less stable when you compare it to a tertiary carbocation. This is what I mean. You are going to understand soon. Just watch. So if I use this now, then it means I'll have CH3 plus, right? CH3 plus. This guy is, is going to be very reactive, that it cannot form. For it to form, it has to be a little bit reactive. It has to be able to wait for what it wants to react to be available. Do you understand now? All right. So what happens is that because there is no heavy group, what does positive charge mean? Positive charge means electron has been lost, right? Okay, so it means that it is looking for electrons, right? So as it is like this, it's called an electrophile. Okay, it's called electrophile because it's looking for electron. Electrophile. Phile means love, filio. Okay, electrophile, loving electrons. So as it is, it wants to seek to coordinate to an electron. Okay, it's looking very reactive, very vigorous. Okay, so because of that, it can almost cannot form compared to this guy, which is a primary carbocation. For example, look at this one now, that has CH and that has CH2 rather, CH3. Now looking at this, you see that this one is bonded already to one carbon. So it's enjoying electron density, electron donation, kind of electron satisfaction, think of it that way, from this one guy. Okay, so it is in level of stability, is more stable than this guy. Okay, so but this one is not even as stable as something like this. We don't need a bond again. Once we put the positive charge, we don't need a bond. Look at this guy, for example, CH3 and CH3. Here's what will happen now. This is what we call hyperconjugation. You know, I mentioned it when I was talking about steric too. Steric hindrance means a hindrance due to bulky group. So when there's bulky group, here's the positive effect. The negative effect is that it will stop any reagent or organogen, we call them organogen. Any organogen that want to attack or react with it, it will stop it. Why? Because it's going to donate electron density that will hinder the electrons of that one from allowing it to come in. Does that make sense to you? But the positive effect is this, that when this guy becomes a carbocation, usually because there is a very electronegative element that is attached to it, which on approaching of a reagent can take on all the electrons. So when it abstracts the electron from this guy will not be alone. It will still have electron to shield that electron deficient center. Does that make sense to you? Good. So this guy here is secondary carbocation. Why? Because it's attached to two more carbons. Then this one here is not as stable as a tertiary carbocation. This is a tertiary carbocation. Why? Because it is bonded to what? To three more carbons. So because of that, by hyperconjugation effect, it will be stabilized. Does that make sense? Now let's go back to what we're talking about. Now looking at this guy, this guy is unlikely. So we use Watt's reaction for higher alkane, and is best for symmetric alkane. If symmetrical alkanes, if you use them for unsymmetrical alkane, you are likely to not get your desired results. Or when you get your desired results, the process of separation is usually not what you want to engage in because it's hard, difficult, okay? All right, this is what I mean. Look at it, for example. If I use, it's best to use haloalkanes. You know, these are haloalkanes that are similar. So if I use, for example, if I use bromoethane, then I should also use plus what? Bromoethane. Then in the presence of this guy, plus Na, and in the presence of dry ether. But if I go and use bromoethane and bromopropane, you know they are different now. I will get an unsymmetric carbon. I'm going to get a mixture of products. Do you understand what that means? See, if I use bromomethane, what's bromoethane, for example? Bromoethane is CH3CH2Br plus, I now combine with bromoethane, bromopropane, CH2CH2Br. Now here's what will happen. It's possible that because their number will differ, okay? So it's possible that this guy and this guy react. When they react together in the presence of Na and dry ether, okay, and heat, what will happen? At the end of the day, you will get CH3, CH2, 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 CH3. So what will they form? 1, 2, 3, 1, 2. That's pent. Pentane, right? Plus 2 NaBr, Br. Okay? Now, please let me check. No. Who's that? Okay, gospel is at the gate. Okay, so where did we stop? So this is for the product of the reaction between these two, okay? Now, what if we have this guy, this bromoethane, react with another bromoethane? What will it give us in the presence of this and this? What will it give us? To give us C for, how do you know? H7Br, Z7, H8, yeah? 1, 2, then 3, H what? 10. Yes, 10. Yeah. How about the BR position? H9. Whatever you count it, 1, 2, 3, 4. That's 10. No? Yeah. Okay. No BR again. No? C for H10. Yeah, is our alkane, yeah? So this is the alkane to form. Do you know what I'm saying? No BR again. Like BR will leave, BR will now combine with Na to form this. Okay, so now look at the product to form. If, because what you combine is this and this, so what could happen inside your system is either this and this combine, or this combine with itself, or this combine with itself. If this combine with itself, what will it give us? 3C3H C3, that's double, that's 6, C6H14. You understand? Yeah? So now imagine you have a mixture of this guy mixed with this guy and this guy inside the solution. So you understand now? So because of that, it's very advisable to use the same alkyl halide to get a symmetrical alkane. Does that make sense? All right, the next one is the Colby's electro. Are you doing chemistry? Okay. There you go for video. Let's go. The Colby's electrolytic process. Now, in this Colby electrolytic process, what do we want to do? We want to electrolyze a salt. That's electrolysis, right? So, which salt are we going to be using? We're going to be using an organic salt. Primarily, we use sodium carboxylate. Okay, let me use ethanoate for this case. So, for example, ethanoate will be CH3CONA. Does it make sense to you? There should be a bond between them. Okay, so what happens is that this is the salt we want to use. Now, once we electrolyze, what do we mean by electrolyzing? We're going to pass electricity through it. Once we pass electricity through the solution of this, first, when this guy gets into solution, let's say this guy gets into the solution, what will happen? By the time it gets into the solution, it dissolves in our solvent, water in this case. Will it be water? Whatever, I think it will be water though, it will be protic. Solvent has to be protic. There's something I want to explain. Do you know protic solvent? We have two types of solvent, protic and aprotic. Protic solvent is one that has proton, that has hydrogen. Aprotic solvent is one that doesn't have proton, okay? So this, once it dissolves, it's going to form this CH3CO minus, yeah? and Na plus. This makes sense, right? So we have our anion and our cation. So this guy will go to where? Cathode. This guy will go to where? Anode. Okay. So and cathode is the negative electrode. This one is positive electrode. So what happens? When this guy goes to the positive electrode, here's what will happen. What happens at the anode? Do you remember? An ox at anode oxidation. Do you remember? Then red cat at cathode reduction. So oxidation, what's oxidation? Leo, loss of electron, oxidation. So loss of electron will happen to our guy here. So what happens? We have our CH3 guy, CH3, CO minus. So it's going to lose electron. I've told you, I probably showed you how to write this here, and you now bring it to the other side here. So you now have CH3CO, so it's going to come here and become plus E minus. So clean it from here. Okay? So now what happens is that the moment this takes place, the moment this guy gains or loses an electron, CO2 is going to form, and we'll have CO2 is going to form. Okay? And we'll have what we call a carbanion. I don't know how to represent this for you. This is a carbanion. Carbon anion. Does that make sense now? Carbanion is just a carbon atom that has more electron than it should have. Okay? So now, once the carbanion is formed, keep in mind that, so this is plus this guy. Keep in mind that there's another guy, maybe two of this guy, for example. So another guy is going to come from another carbanion, and this carbanion will mix with the other carbanion. So we have R and the second R. They will come together, and what will they form? They will form your alkane, given that they are different, for example. Does that make sense? Okay. Then at the cathode, this guy will migrate to the cathode. Okay. Then I don't know which one will be preferentially discharged. Either this is preferentially discharged or it is preferentially discharged to give water, depending on other electrolytic properties. But these are major products, yeah? That makes sense, right? So what will happen is that if this guy is not preferentially discharged, you're going to have this guy will now come and react to this guy. So the overall reaction is that you have this guy plus we need this guy, right? So when it breaks open, it's going to give us, so what is it going to react with? This guy. Okay, how did we even achieve this first? Is trying to look for a way to combine that. Okay. So that at the end of the day, what we'll have is, okay, plus, we had the acid first, so we combine with NaOH, then we had this, okay? So at the end of the day, when this reacts with this, it will give us the salt. That's what I showed you. Then you will now have Na2CO3, yes, this is what I was looking for. N plus CH3, C. Okay, for with Kolbe's electrolytic process, this thing formed is usually a carbon less than the original substrate, because it will lose this carbon to this place. Does that make sense to you? All right. So that's the way it is. So that's that for Kolbe's electrolytic process. Then the next one is we have talked about halogenation. We've not talked about the Clemmensen reduction, have we? No, right? Let's talk about Clemmensen reduction. No, let's talk about this one. This one is fast and soft and interesting. Grignard reagent has a general formula. So very simply, what do we want to do first? We want to first combine our hydrogen, our alkane with, we want to use our alkane with magnesium, they are already combined, okay? They'll be combined with an halide, they react an halide and they'll form RMgX, okay? So this one, in the presence of a weak acid and aqueous medium, will now form our what's it called? Our alkane plus MgOH X. Okay, so that if we have, let's say, let's put 2 here, so that this will also be 2, X2. I don't know, maybe they will put the 2, let's put it here, because that's how we write these guys. So if we have, for example, 2CH3 Mg here, plus, let's say Cl or Br2, for example. We use Br a lot because of its degree of reactivity. It's not as vigorous. We can't even use fluorine at all, okay? All right, so what we'll have is R CH3, 2CH3 Mg and Br. So by the time this guy reacts with proton and the other guys, water, what will happen is that we're going to form CH3 and MgOH Br. So this is our this one here is our Grignard reagent. This is the formula. Okay, RMGX. Then so that's that for Grignard. So let's talk about let's talk about which one? Clemency reduction. So I'll talk about the Wolff-Kishner. Now for the clemency reduction, I don't even know if it's E or N. Oh, clemency reduction. Now that's just the reduction of an aldehyde. Okay, an aldehyde or a ketone will be reduced. Now, how does this reduction take place? It takes place in the presence of a conc acid, zinc amalgam, and that is just Hg, and you have zinc amalgam, and that's basically it. And that guy, HCl, and the HCl must be concentrated. Here's the reason. So let's use, for example, acetone, propanone, for example. And in fact, this clemency reduction is also used for preparing cyclic hydrocarbons. Okay, but it's going to be used here. It will be used for cyclic by diacetones. Does that make sense to you? Like, see, an acetone that has the carbonyl carbon on the 2 ends, so it will cyclize. So when it cyclizes, I'll try to show you if I can. I don't know if I still know. So this is it. So by the time, what happens is that this guy is going to protonate this guy. So once it protonates it, then you have, let's just say RC11O, R, they are the same in this our case. So once it protonates it, what is that? Okay, so once it protonates it, then it's going to form a radical that is, no, not a radical yet, it's going to form a carbonyl carbon that is a carbocation. Carbocation, why? Because it has gained more, see what to form, something that looks like this. Okay, then our R. So why has it become positive charge? Because it has gained this oxygen, this guy is having more what's it called, bond than it should have around itself. Does that make sense to you? So what will happen is that at the end of the day, by continuous, so what will happen first next is that this zinc is going to lose electron and give that electron to, actually it loses 2 electrons, okay, but it's 1 electron that will come and be added to this guy. And on the, but the moment this guy takes that 1 electron, it becomes a radical, okay? And when it becomes a radical, it becomes very reactive, and then on further protonation, on further addition of hydrogen, is going to form RCH and CH2 and R. So this guy, the radical point portion will be, protonated more, and this one will be taken away as water. Okay, so we have aldehyde plus this to give the corresponding this thing. So you just say CH3 in this case, CH2, CH3 plus H2O. Okay, so that's the Clemenson's reduction. Wolff-Kishner reduction is almost the same, okay, only that the difference is this. This one takes place in an acidic medium, while this one takes place in what? Basic medium. It uses a base instead, KOH to be precise, KOH. So that's a strong base here. So the last one we'll see is, that's all right, we've seen this. Okay, decarboxylation. Decarboxylation is just, we want to remove the carboxyl group of a salt, all right? So first, how did we form the salt? Let me start from there because that was what we didn't do in the other one. So for example, I have my salt, ethanoic acid. I'll combine with the sodium, soda lime. What's the soda lime, right? Caustic soda, right? And with quicklime. Okay, so this lime, the soda portion of this and the lime portion of this is what is called soda lime. So these two together is called soda lime. Okay, so they combine together. So soda lime. So once you react this guy with this guy, we will now have our salt that we want to decarboxylate, NH. This one will lose the hydrogen and form water. So once we have this, we want to decarboxylate this. Now, how do we decarboxylate this? The OH portion of this guy is going to attack this guy. I don't want to be showing this thing again, but what happens is that after attacking this guy, the carboxyl group is going to leave. Okay, once the carboxyl group leaves, then you are going to be left with the carboxyl group will leave. You are going to left with CH3, just like the electrolytic process that we saw the other time. CH3 radical, no, in fact, not radical, a carbon ion, and the other one too. Another one, let's say it was 2, so 1 and 2. So both of them will now come together again to form CH3. So you see this one to form symmetric carbon. Is it clear? Let me just show you the general formula. Once this occurs, what will happen is that we'll have Na and CO3, COO. So that becomes Na2. So we put 2 here to CO3. Does that make sense? Na2CO3. Okay, no, this is not from here, we'll write it from here. This one will react further with this guy. I just so that it will make more sense. You understand? On the first reaction, it will form this salt. Then on further reaction, then we'll take this guy, CO3. Does that make sense? Okay, so what will happen is that, okay, what will form is RH. So at the end of the day, what will form is RH. Okay, it gets protonated. What will happen is that the carbon ion that is formed here, I remember now, the carbon ion that is formed here, it will not form with another carbon ion. What will happen is that it will come and take proton from inside the solution. Do you understand that? So it means this also takes place in a protic solvent. So it will take proton from the solution and to form CH4, for example. Does that make sense? All right. So that's the case. So that's the carboxylation. Should we quickly rush on the chemical properties? Chemical reaction. All right. So what are the chemical reactions that are same with these guys. We have the first and most common one is the combustion reaction. Okay, then we also have the substitution reaction, and that's like hydrogenation. Okay, substitution by halogenation. Now keep in mind that most of these reactions are catalyzed. Just like we have here, there are also catalysts around here. Catalyst. So what other reaction do we see with these guys? We have nitrate, nitration reaction. We have isomerization. We have aromatization. And we have pyrolysis. Okay. Now, here's what happens. Now with combustion reaction, the general formula for combustion reaction of alkane is when you have a CnH2n plus 2 wanting to react with oxygen, the amount of oxygen to react with is given by the formula 3n plus 1 over 2 O2. Okay, then plus I think NCO2 plus N plus 1 H2O. Let's verify this. Let's use propane, for example. That's 3. N will be 3, right? So that will be C3H8, yeah? Plus 3 times 3, 9 plus 1, 5. So that will be 5O2 to give, you understand what I'm doing? Okay. 3CO2 plus 4H2O. Let's see. 4 hydrogen, 8 hydrogens, 8 hydrogens. 3, 3, 4 oxygens, no, 6 oxygen, 4, 10. So it means the formula is correct, right? So this is the general formula for the combustion of alkanes. Generally, all alkanes, all organic compounds, once they engage with combustion reaction with oxygen, as far as it's not a controlled combustion reaction. For controlled combustion reaction, we have other things that we can form. We can form acetone, okay, aldehyde and ketones, okay, under controlled oxidation, and that one will need other catalysts, okay, we need catalysts. But for general combustion reaction, for all organic compounds, you always form CO2 and H2O. All right, so substitution reaction. Now, what happens with substitution? We just, for example, in this case, we want to use halogenation. Now, for this to take place, there are 3 steps. It takes place in a 3-step process. We have the initiation, the propagation, and the termination. And when you get to this and you want to do more organic chemistry, you are going to see this a lot, this step. Now, the initiation process is where the, here's what we want to form. We want to use, what do we want to do? We want to, okay, we have our, for example, let's say CH4, for example. We want to add bromine to it, for example, Br2. The first thing that happens is there is homolytic fission of this guy. You understand what that means, yeah? So, and once there is an homolytic fission, first, what creates the possibility of that homolytic fission? Ultraviolet ray is a catalyst. UV light is a catalyst. So, or sunlight. Okay? But when you say sunlight, it's just the UV wavelength. Okay? So, what happens is this, that there is equal sharing of the electron. So what happens? Then a very reactive radical is formed. So these radicals are now able to break the bond here. So actually when they break the bond, they don't attack at the same time. Okay? So this is the rate determining step. It's the initiation stage. Homolytic fission first. Then we now see CH3 bond with one of the BRs. Then the second BR will bond with the hydrogen that left. Does that make sense? Then this one again will occur again. This thing keeps forming. These radicals keep forming, and then it will keep taking place like that. Okay? All right. So that is so then the termination. So the degree in which they take place, it will be the speed at which they take place will be reducing. Okay, the more of these levels they are forming, the more substitution that is happening to this guy. Okay, it will be slowing down until the termination stage when all of the hydrogen have been substituted. All right. So at that stage we have CBr4. Then the next one is nitration. Nitration is fairly simple. It takes place in the presence of. So I had to stop it. Okay, so the nitration is quite easy. What happens is that our alkane will react with HNO3 and form different types of nitrates. Okay, it's in the presence of KOH though. Is it KOH? Is it KOH the catalyst? I think so. For nitration, I think so. Is KOH the catalyst? Yeah. So this guy will form RNO2 and this one will form R prime NO2. Does that make sense? Depending on what and what you have each. Then plus H2O. Alright. Then for isomerization is just the rearrangements, okay, that happens. Is used to increase the octane rating. So which of these chemical reactions is used to increase octane rating of your whatever isomerization? So for example, we have a particular N-pentane, for example. It will undergo isomerization in the presence of the following catalyst. Do I still remember? The catalyst that I think they are AlCl3, HCl, and one more like that. So in the presence of this catalyst and heat, of course, heat is going to isomerize. So it could give you maybe isopentane. Okay, it has isomerized. You know what isopentane is? Okay, so it has isomerized. It's not isomerizing. You know iso group, yeah? That looks like Y. Good. You know tat group. You know new group. New. And new is like this. That is longer. Okay, so then we have aromatization. Aromatization is just when we have a cyclic or a non-cyclic. So we have a cyclic or acyclic hydrocarbon isomerize. So if it was an acyclic one, it will first undergo cyclization before the aromatization takes place. Okay, the guy will be heated to very high temperature, and then it's going to form benzene. It's going to form benzene and benzene products, other benzene type products. Okay, so usually the best thing they use is hexane or cyclohexane. So if it's hexane they are using, they will first cyclize hexane, so to form cyclohexane by release of CO2 to release. Generally, in fact, alkanes, because the longer the chain, they begin to they are able to by themselves, not by themselves, they are easy to cyclize the longer the chain. Okay, they're easy to cyclize. So this guy will cyclize and then will form benzene under high pressure and what? High temperature. The temperature is usually greater than 500 degrees Celsius. Then for pyrolysis, at temperature greater than 600 degrees Celsius or 700 Kelvin, 770 Kelvin. Okay, so that thing is 273, right? So it's greater than this guy. So that is where pyrolysis takes place. The word pyrolysis is going from two Latin words. Pyre means fire. And what does lysis mean? cleavage or break, right? So what happens is, it's also called, pyrolysis is also called cracking. Okay, so for example, we can have C10H what? H what will it be? 22. It can break down to C5H12 and C5H, how many remain? 10. So what would this be? Pentane and what? Pentene. You see that? Alright. In the presence of catalyst too, isomerization takes place in the presence of catalysts such as vanadium 5 oxide, okay, while pyrolysis takes place in the presence of catalysts like Al2O3 with intense heat. Take note of the heat. Alright. So that will be it for this video. Do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you. Do you understand it all? Alright.